And this could lead into a different type of problem. So the probability of making a type 1 error is alpha. So if you do a bunch of tests, you're going to find significance in alpha of them just by chance. So let's say you did 100 tests, you should expect to find 5 of them as significant just by chance. And we call this the problem of multiple testing. And that means if you do multiple tests, you're probably going to find things that look significant just by chance, and you're going to make a type 1 error. And there's a related problem known as publication bias, which is that researchers, when they do studies, if they find something that's significant, then they can often get that published in a paper and talked about in the news and things like that. But if the results aren't significant, it's hard for them to get published. So only the things that look significant get published. And there's a webcomic called XKCD that has a comic that is about this particular problem. It's kind of long, so I'm going to open it up and scroll through it on my iPad. Okay, so here we are on this comic website. It starts off with a person saying, jelly beans cause acne. So maybe someone has an idea, they have a hypothesis, and the other person says, scientists, investigate. The scientists say, but we're playing Minecraft. Fine. They go do the study and they come back and they say, we found no link between jelly beans and acne. Our p-value was greater than 0.05. That settles it. I hear it's only a certain color that causes it. Scientists, but Minecraft. And so now they're going to go through and do a bunch of studies. We found no link between purple jelly beans and acne. That p-value was large. No link between brown jelly beans and acne. No link between pink jelly beans. None for blue, none for teal, none for salmon, none for red, none for turquoise, magenta, yellow, gray, tan, cyan. We found a link between green jelly beans and acne. P is less than 0.05. Whoa! No link between mauve jelly beans and acne, beige jelly beans and acne, lilac, black, peach, orange. And then the news story says, news, green jelly beans linked to acne, 95% confidence, only 5% of a coincidence. So this is the problem of multiple testing. They did, I think it was 20 tests here. Let's see the array of panels on the cartoon, 1, 2, 3, 4, 5 across, and 1, 2, 3, 4 down. So they did 20 studies, and they found one that was significant. 1 out of 20, that's that 0.05. So just by random chance, we'd expect to find one significant. And so probably they're just making a type 1 error there, and it really should not have made the news. So these two issues can work together. So alpha of all the tests show significance just by chance. Things that look significant get published. And that means that a fair number of things that get published are actually false. So that's kind of scary. And there's a number of solutions to fix this problem. So if you are doing research, you should make sure that your results can be replicated, done again to find the same result. So Model did this with the politics and gray study. He found that really small p-value and he thought, well, I better replicate it just to make sure it's real. And he found out it was just probably random chance that first time. And then the other thing is publish the code that you used to find your results and the data that you collected so that others can look at your work. So this is called reproducibility. And so if you're just someone who's reading statistics, you should really be skeptical about claims that are one of many tests. So if you see something that says, we looked for a connection between all of these genes and, liking broccoli, that's probably that they just did many tests and they found one that looked significant by chance. And you should also look out for replication and reproducibility. So if someone says, we replicated this multiple times, that's a good indication that it's really a true finding. And if they say, we've published our code and data so you can look at it, well, you should look at it to see if they actually did the right stuff. But just making it available is a pretty good sign that they did things right because they're willing to be transparent. So that was kind of about type 1 error. There's also type 2 error, and that's where we failed to reject the null, even though the alternative was the thing that was true. And we can reduce the probability of making that kind of error in two different ways. One would be to increase the significance level. So if instead of using alpha equals 0.05, let's go and say, let's use alpha equals 0.1. If we do that, we're going to make a type 1 error more often, but we're going to make the type 2 error less often. And the other thing that we could do is increase our sample size. So let's say that we have a study with 100 people in it, and then we're able to move into a study with 1,000 people. We're going to be able to reduce the probability of making that type 2 error. So you can think about this alpha level as sort of like a line in the sand. So if you're less than alpha, then you're going to reject the null hypothesis. But if you are greater than alpha, you're going to fail to reject. If you're on this side and you've rejected the null, you could be making a type 1 error if the null hypothesis is true. And if we fail to reject, we could be making a type 2 error if the alternative hypothesis is true. So we could move around this line, the alpha line, right? We could make it smaller or bigger depending on what was the most important to us. If type 1 error is really bad, you should decrease alpha. And if a type 2 error is really bad, you should increase alpha. And the problem is you can never not make any errors. You have to decide which of those types of errors is worse to you. So let's look at the relationship between sample size and errors using StatKey. So here we are on StatKey. I think I'm going to look at the sampling distribution section and click on proportion. And then I'm just going to do something pretty basic. I'm going to do coin flips. So I want to know if the probability of getting heads is really 0.5. And I could say that I want to take samples of size n equal 10. So I'm going to click up here at the top where it says choose samples of n equal. I'm just going to do samples of size 10. And then let's do 1,000 of them. So here we are with 1,000 samples. Maybe I'll smoosh it down a little bit. So let's say that we observed a proportion of 60% heads. So let's do a right tail and then change this number to 0.6. Okay? That p-value is going to be pretty big, 0.384. And I'll take a screenshot of that. Versus if I decided to make those samples of size 100, so instead of 10, let's put 100 back here. And again, let's do 1,000 samples of size 100 and do a right tail. It looks like it defaulted to 0.6 already. That's a much smaller p-value. We'll take a screenshot of that one as well. So in this example, the null hypothesis was that the true proportion was less than or equal to 0.5. The alternative hypothesis was the true proportion was greater than 0.5, and we observed a p-hat of 0.6. So I did this twice in StatKey, and both times I did 1,000 samples. So 1,000 samples. Both times I looked out 0.6 and I wanted to see how much of the distribution was as extreme or more extreme. So again, 0.6 here, as extreme or more extreme. So the only thing that was different between these two was the choosing samples of size n equal 10 or choosing samples of size n equal 100. So the larger sample size makes it easier to reject the null. So we got a much smaller p-value just by taking larger samples. And this is something to remember if you're ever working with really big data, like you're working for a corporation and looking at user behavior of hundreds or thousands or millions of users. You're probably going to find things that look significant just because you have a really big sample size. And then the last thing that I want to talk about is the idea of statistical significance versus practical significance. So sometimes you'll find something that's very statistically significant, but not practically significant. So the example that I always give is that there are statistically significant differences between people who identify as men and people who identify as women on their SAT scores. So women tend to score better on the verbal and men tend to score better on the math. And it's statistically significant, really small p-value. But it's not practically significant because it's only a difference of like part of a point on the whole SAT. So I have this little cartoon by Allison Horst, who's a data scientist who does illustrations, and she's got the p-value hogging the mic while the context is lurking in the background, really sad. There's also this idea of effect size, which is a little bit outside the scope of the class, but this is a better thing to use than strictly a p-value. An effect size is going to contain both statistical significance and practical significance, kind of in the same number.